Definition of the scalar dot product. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on the fundamental operations of vector algebra, specifically learning the mechanics of how to add and subtract vectors. Now, as we move forward, we encounter a new challenge. When we talk about multiplication in vector algebra, we must be careful. It is not quite as straightforward as the multiplication of real numbers that you are used to. In the world of vectors, multiplication isn't just one single operation. There are actually two distinct ways to multiply vectors. Today, we are going to introduce you to the first of these methods, the scalar product, which you will also frequently hear referred to as the dot product. Understanding the concept. Now that we've established that vector multiplication isn't as straightforward as the addition or subtraction we studied previously, let's dive into what this operation actually does. First, it is crucial to understand that the scalar product is a mathematical operation that takes two vectors as inputs, but instead of producing a new vector with a direction, it returns a scalar, which is simply a real number. This is the fundamental reason why we refer to it as the scalar product. To visualize this, imagine you have two vectors, vector A and vector B. Rather than just looking at their lengths, think of the scalar product as a way to measure how much one vector overlaps or acts in the same direction as the other. It essentially tells us how much a vector A is pointing along the path of vector B. We will see the precise formula to calculate this overlap in the next slide. The mathematical definition. Now that we understand the concept of how vectors can overlap, let's look at the actual mathematical definition. For two non-zero vectors, let's call them vector A and vector B, the scalar product is defined by a specific formula. We write this as vector A dot vector B, which is equal to the magnitude of vector A multiplied by the magnitude of vector B, all multiplied by the cosine of theta. To make sure we are all on the same page, let's break down each component of this formula. First, when you see vector A dot vector B, that dot symbol is the standard notation we use to represent the dot product itself. Next, we have the vertical bars around vector A, which represents the magnitude, or simply the length, of vector A. Similarly, the vertical bars around vector B represent the magnitude of vector B. Finally, we have the symbol theta. This represents the angle between our two vectors. It is important to note that when we calculate this, we measure the angle theta such that it stays within the range of 0 to pi radians, which is the same as saying 0 to 180 degrees. Keep this formula in mind, because in the next slide, we will discuss what happens to this calculation if one of those vectors happens to be a zero vector. Special case, zero vectors. Now, before we move on to some practical applications, we need to address a specific edge case regarding the formula we just discussed. In our previous slide, we saw that the dot product relies on the cosine of theta, which represents the angle between our two vectors. However, in mathematics, an angle can only truly be defined when both vectors have a specific direction. If we encounter a situation where either vector A or vector B is equal to the zero vector, we run into a problem because the zero vector has no magnitude and, more importantly, no direction. Since the direction is undefined, the angle theta becomes impossible to determine. To keep our mathematics consistent and avoid any errors in calculation, we follow a mathematical convention. In these specific cases, where at least one of the vectors is a zero vector, we simply define the scalar product of vector A dot vector B as being equal to 0. This ensures that our operations remain smooth even when dealing with the zero vector. Real-world example, work done in physics. The most common application of the scalar product in physics is calculating something called work done. In physics, we say work is being done when a force causes an object to move over a certain displacement. To make this concrete, let's look at a specific scenario. Imagine a person pulling a heavy crate across a flat floor using a rope. The person pulls the rope with a force, which we will call vector F, at an angle, theta, relative to the horizontal floor. Meanwhile, the crate moves a certain distance along the floor, which we will call the displacement vector, d. If you want to calculate exactly how much work was performed, you can follow these 5 steps. First, identify your vectors. We have our force vector, F, and our displacement vector, d. Second, determine the magnitudes. You need to find the strength of that force, which is the magnitude of F, measured in newtons, and the distance the crate moved, which is the magnitude of d, measured in meters. Third, identify the angle, theta, which is the angle between the rope and the floor. Fourth, apply the scalar product formula we learned on the previous slide. The work done, which we represent with a capital W, is the dot product of force and displacement. Mathematically, this is written as W equals F dot d, which expands to the magnitude of F, multiplied by the magnitude of d, multiplied by the cosine of theta. Finally, interpret your result. Notice that the resulting value, W, is a scalar, a simple real number measured in joules. It isn't a vector because work represents a quantity of energy, and energy doesn't have a direction. Now that we have mastered the mathematical definition and the special case of zero vectors, let's see why this concept is actually useful in the real world. This brings us to an important point. As we move to the next slide, be careful not to confuse this scalar result with other types of vector multiplication. Common mistakes to avoid. Now, before we wrap up today's lesson with our summary, I want to pause and highlight some common pitfalls. I've seen many students lose marks on exams by making these specific errors, so please pay close attention. First, be very careful not to confuse the scalar product with scalar multiplication. It is easy to mix these up when you are working quickly. When we write a dot b, we are performing the dot product of 2 vectors, which, as we discussed in the earlier slides, results in a single real number. However, when you see k times vector a, where k is a constant, that is scalar multiplication. In that case, you are scaling the vector, and the result is still a vector, not a number. Always check your output. If you expect a scalar but get a vector, you've likely performed scalar multiplication by mistake. Second, a very frequent error is forgetting the cosine term in our formula. It is tempting to simply multiply the magnitude of vector a by the magnitude of vector b, but that only gives you a partial picture. As we saw in our definition, the dot product depends heavily on the angle theta between the 2 vectors. If the vectors are not pointing in the same direction, the cosine term will scale that product down. Without the cosine of theta, you aren't calculating the dot product, you're just multiplying their lengths. Finally, keep an eye on your angle range. When calculating the dot product, we always define the angle theta to be between 0 and pi radians, or 0 to 180 degrees. If a problem provides you with an angle outside of this range, you cannot plug it directly into the formula as is. You must first find the equivalent angle within that 0 to pi interval. Keep these 3 points in mind, and you will avoid the most common mistakes in vector algebra. Key takeaways. First, remember the fundamental nature of this operation. The scalar product of 2 vectors does not result in a new vector, but rather in a single real number, which we call a scalar. This is a crucial distinction to keep in mind. Second, let's revisit the mathematical definition. The dot product of vector a and vector b is equal to the magnitude of vector a, multiplied by the magnitude of vector b, all multiplied by the cosine of theta. Third, regarding the geometry of the operation, always remember that the angle theta is restricted to the interval from 0 to pi, or 0 to 180 degrees. This ensures our calculation remains consistent. Fourth, we touched on a special case earlier. If either vector in your calculation is a 0 vector, the dot product is simply 0. Finally, to give you a deeper conceptual understanding, think of the dot product as a way to calculate the projection of one vector onto another, and then multiplying that projected length by the magnitude of the second vector. This overlap concept is exactly what we discussed when looking at the physics of work done. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. If you have reviewed these points and feel confident, you are ready to tackle the next topic. Great job today.